Assalamu alaikum and good day everyone. I'm your teacher Muhammad Ikram from Pakistan International School Taif KSA. I welcome you all into my today class. Today is our lecture number 3rd. And this lecture number 3rd is about the Coulombs Law. In my previous lecture, I introduced to you about the properties of the charges. And the most significant part, the most important point there was that charge is the intrinsic, basic, or natural property of the electron or proton, where when they come close together, then they create or they exert a force. So it is because of the charge where the charge particle or the charge bodies exert electrostatic force of attraction or repulsion, to which I introduced to you in my earlier class. In our today class, I will explain you the Coulomb law because you know that physics believe because you know that physics believe on quantities being measured. So if there is an electrostatic force of attraction or repulsion between the charged particle, then what will be the magnitude of that force, on which factors that force will depend. So here I will explain it to you in my this lecture. Moreover, you have learned about the Coulomb's law in class 10 also. Here I will introduce to you to the Coulomb's law in a different perspective. They three, four important points regarding the Coulomb law I will explain to you. The Coulomb's law, they, that is the it was first stated by Sir Austin D. Coulomb. He was French mathematician and physicist, and he was the first to found a mathematical relationship for the force that exists between two charged particles. Here, the Coulomb's law, when I explain, first I will explain it to you for the Coulomb law in free space. In free space, right? That is then the Coulomb's law for the material medium. Material medium. And third, I will explain about relative the relative permittivity. Permittivity. I will explain this. The relative permittivity, or that is what we can call the dielectric constant. I will explain to you this also. And then another one is the Coulomb's law in vector form. Coulomb's law in what? In vectorial form or in vector form, since force is a vector quantity. And for the senior classes, it is mandatory that we should know how the Coulomb's law can be expressed in a vector form. Now, the Coulomb's law, physically, this law states that physically, this law states that the the electrostatic force of attraction or repulsion between two point charges between 2 point charges is directly proportional to the magnitude of the product of charges of the product of charges and inversely proportional and inversely proportional to the square of the distance, square of the distance between their centers, between the center of the two charges, between the centers of the 2 point charges. Few points which I would like to explain to you. The first one, that what are point charges, right? And second, the square of the distance between their centers. This is mandatory. Distance between their centers. Why? Because it is always center to center distance which matter, right? And I'll be telling to you why. Now, what are the point charges? I'm coming to that point also. Mathematically, we can write that. So, mathematically, mathematically, we can write that if we have 2 point charges. For example, let's say if we have one this charge, say positive charge Q1, and if we have another this charge, let's say another charge Q2, the 2 point charges. Now, what are point charges? Point charges are in fact the two charges are said to be point charges if the distance between the two charges is smaller than the dimension of each charge, then we call them the point charges. Now, if these two charges are separated at a distance r, let us say this is the distance between their centers, right? This distance r. So they are separated at a distance what? At a distance r. The distance between the two charges, between the two charges is this distance r. Now, Coulomb investigated that the electrostatic force of attraction is directly proportional to the product of the magnitude of the product of the two charges. It means that the force does not depend on the magnitude of one charge. It depends on the product of the two charges. For example, if you have this charge, let us suppose, for example, say if you have this 200 coulomb of charge, and let's say if this is 100 coulomb of charge, then which one exert more force on which charge? So they exert the same force on each other. It does not depend on the magnitude of either of the charge. It depends on the product, right? So this is why it is not important, right? It depends on the product of the two. One is this. This is equation number one. Number two, this is inversely proportional to the square of the distance between the two charged particles, right? Second important point which I want to tell you, that look, there is this force which I want to label it in a way like this. If this is charge Q1 and this is charge Q2, so let's say we have one this force, since the two repels each other, and here we have one this force, right? So this is the force. We call this force as one force 1 2, and we call this force 2 1. Now I will write it like this: F1 on 2. That is, it is the force which the charge Q1 exerts on Q2. And this force is what? Repelling force, so it tries to push it. Why? Because both charges are like charges. And you see, this is the force which the charge 2 exert on the charge 1. Now here's the Newton third law of motion is also valid. And if you see this, these two forces, that is, look, these two forces, that is 1 on 2 or 2 on 1, they are the same in magnitude, but what? Opposite in direction, and they acts on two different charged particles, right? But they have the same magnitude. Let I call this as the electrostatic force. And this electrostatic force acts along the line joining the center of the two charges. The center of what? The center of the two charges, right? So that force acts along what? That force acts along the center joining the two. This is why we will use this as in the vectorial form like this. For example, this is what? This is the position vector between the charge q1 and the charge q2, which is completely along the x-axis, and we will denote this by a vector, unit vector, and you know much about the unit vector from the previous class. That is from 1 to 2, a unit vector along the direction of the displacement r. This is a unit vector, right? So the force is along this unit vector, along the line joining the center of the two charge particle. And now the medium between the two charge particle, this medium is what? The medium is a free space. The medium between the two charge particle is what? It is the medium between them is, this shows that there is what? That there is a free space between the two. There is no medium. This uh, suggests a free space, right? So this is what? This is the free space. The medium is what? Free space. You may consider as vacuum. Right now, combining these two equations into a single equation, then what does this mean? That this electrostatic force is directly proportional to what? It is directly proportional to Q1, Q2 into what? Into the 1 over r square. Or we can write that the electrostatic force is equal to K into Q1 Q2 by R square, where you know about K, and that K was in fact what? K is the electrostatic constant. This K is what? K is the electrostatic constant. Electrostatic constant. That is what? The electrostatic constant. And if you remember, your class 10 and your teacher directly told you that its numerical value is 9 into 10 to the power 9 Newton meter square per Coulomb square, right? And that was finished. Here I would like to tell you that this K is the electrostatic constant, but this K, it is not a pure constant, right? Because it depends on some other parameters. And what are those other parameters? That is This K experiment determines the value of this K is 4 pi into what? Into epsilon naught. Right now, what is this epsilon naught? The 4 pi into epsilon naught. This epsilon naught, we call this epsilon naught is what? This epsilon naught. This is called permittivity. Permittivity of the free space. Free space. Now, what does really this permittivity means? Few important things you should know here. Permittivity means it is the strength of the medium. It is the strength of what? It is the strength. This is the strength of the medium to exchange the electrostatic force. So one important point here we should know is this thing makes the electrostatic force medium dependent. Makes the electrostatic force what? The electrostatic force medium dependent. Medium dependent. Why? Because this, which we call the permittivity of the free space, it purely depends on the nature of the medium. The nature of the medium that is present between the two charged particles, whether it is vacuum, whether it is air, whether it is water, glass, or whatsoever. This is why this force is what? This is why this force is medium dependent. It is what? It is medium dependent and purely depends on the medium. Unlike the gravitational force is medium independent, while the electrostatic force is medium dependent. But the electrostatic force of attraction or repulsion, this force is much more stronger than the gravitational force. Why? If you compare gravity, let me do it for you here. If you compare, look, if you have the gravity, you see here, and contrary to this, you have the electrostatic force. The electrostatic force. So if you compare gravity, look, what was the value of this G? 6.67 into 10 raised to the power minus 11, the numerical value, Newton meters square per kilogram square. And here, what is the value of this K? This value of this K is 9 into 10 raised to the power what? 9, right? So that is Newton meters square per coulomb square. So you see that, look, this is very large than this. This is why this makes the electrostatic force much more stronger than the gravitational force. And I would like to give you a kind of home assignment. And your assignment is that if you have two bodies, one each 1 kilogram masses, right? And in two bodies having masses, or two pairs having mass 1 kilogram. If they are separated at a distance 1 meter apart, or the distance between their center is 1 meter, right? If they are 1 meter apart, then and if each pair has 1 coulomb of charge on them also, then calculate the ratio of the electrostatic force to the gravitational force, that which force is stronger and by which factor. You do that. Second important point, I told you that, as I told you, that the center to center distance is important. Why? Because now you do understand, if the distance between these two, if the charges are very much close together, for example, shoulder to shoulder, let us suppose, then what you will say? You would say that the distance between the charges are zero. So the force will become infinite. And they wouldn't be able, the two body wouldn't be able to remove. For example, if you have one this body, and you have another this body, body A and body B. And if they both have the charges on them, and if you bring them close together, so that if you consider them no distance between them, for example, if they just touch each other, then still there is a distance between them. Why? Because center to center distance is important. If you don't take it into notice, then what will happen if you just bring them close together like this? For example, if they just join each other, and if you say the distance between them is 0, then what will happen? The force will become infinite and the two bodies cannot be separated, which is not the case. You can see the two charged bodies can easily be then separated, right? If they have unlike charges on them, for example, this is plus and this is minus, right? So the electrostatic force of attraction will be infinite if you consider the distance between them 0, such as in this case. So this is why center to center distance is always important. So the center to center distance is measured here. Now let us come back to the permittivity of the free space. That what does the permittivity of the free space means? As I told you, that it is the strength of the medium to exchange the electrostatic force between the two charged particles. This numerically, this epsilon naught, it is equal to what? This epsilon is equal to 8.85 into 10 raised to the power minus 12 coulomb square per newton per meter square, right? That is the numerical value. This is also equal, sometime we can say this is equal to 8.85 into 10 raised to the power minus 12 farad per meter. And I leave it upon you to find that how the Newton, the Coulomb per Newton per meter square is equal to farad per meter. So these both are the SI unit. Usually this is much more standard. These both are the SI unit of what? The SI unit of the permittivity of the free space. So that is how we can write the value of this. And how you can get this, for example, this is so easy. How it is easy? Let us see. Look, what will be your this epsilon naught? It could be equal to what? It could be equal to 1 over 4 pi into k, and you already know the value of the k, which is like here like this. So you just see and you will find it like that way. Okay, so it is Newton, the it is 8.85 into 10 to the power minus 12 coulomb square per newton per meter square or farad per meter. That is what I like the most. So this is how the Newton sorry, this is how the Coulomb's law is. Now you see that it has been done for what? For in free space. And then now let us do it for the material medium, that how it can be done for the material medium. For the material medium, we use the Coulomb's law for the material medium is like this. For example, if we have what? That is that look, for the Coulomb's law, that is since uh, for the free space or for vacuum. For the vacuum, we have found that it is 1 over 4 pi epsilon naught into Q1 Q2 by R square. We have won this for the vacuum. Now for material medium, if there is medium other than air, for material medium, for what? For the material medium, then how we can express like this? For example, if there is a medium other than vacuum, for example air, between the two charged particle, then how we can write? Then the Coulomb's law will take the form. The Coulomb's law, the Coulomb's law will then turn into what? F for material medium, it will become like this: 1 over 4 pi into epsilon into Q1, sorry, into Q1 Q2 by R square, where this epsilon is the permittivity of what? permittivity, permittivity, it is the permittivity of the medium present between the two charged particle of the medium, between the two charged particle, right, as compared to that of the vacuum. So we have now won this thing. Is it clear? So this is now very important relationship here, and we now want to define another one. Is I told you here about what, about the relative, this has been done. Now the relative permittivity, that what is that relative permittivity? So for the relative permittivity, we can define the relative permittivity as like this. Relative permittivity. Permittivity. Now, what is relative permittivity? Relative permittivity, it is defined as, it is the denoted by ER, and it is the ratio of the permittivity of the medium when there is a medium to that of what, the ratio of the permittivity when there is a medium between the charge to that of when there is no medium between the two charges. So this relative permittivity, it can be used to calculate what, it can be used to calculate the permittivity of any medium. So moreover, what we can write, that keeping this thing into in mind, we can write that this permittivity of the medium can be expressed in terms of relative permittivity and into the permittivity of the free space. So this is also one of the important equation, and this will help us in calculating the relationship for what, for the F medium and FEQ. For example, here now if I just want to find the relationship, a very important relationship, for example, the relation between what, it is another important point, the relation between the relation between relation between F medium, F vacuum, the electrostatic force when there is vacuum between the charged particle, and this relative permittivity epsilon r. So I will explain this to you, that what is the relationship between these, and this is important. This might be one of the question maybe in your paper also. They will ask you to find this relationship, and this is very easy as eating ice cream. For example, let us see, as we know that as we know that we know that the permittivity between lock, when there is a medium F medium, we can write that it is equal to what, 1 over 4 pi into epsilon into Q1 Q2 by R square. So you see, look how I can write it like this. You see, it will be 1 over 4 pi into, what is this epsilon? This epsilon is equal to epsilon naught R into epsilon naught into what? Into Q1 Q2 by R square. Rearranging this equation, F medium will be equal to, it will be equal to 1 into epsilon naught R into what, into 1 over 4 pi into epsilon naught into Q1 Q2 by R square. So what does this means? This implies that F medium equals what? Look, 1 over epsilon naught R, and this is for FEQ, because in the beginning we consider for the VQ our free space is 1 over 4 pi epsilon naught into Q1 Q2 by R square. So what does this means? This means that F medium is equal F vacuum divided by epsilon naught R. Now, since epsilon naught R is always a greater than one, a number greater than one, so what does this means? What is the result? The result is very important. The result is that F vacuum, if you just write, look, what does this means? F vacuum. F vacuum is equal to epsilon naught R into F medium, like this. So what is this result? The result is that F vacuum is always greater than what? F medium. What does this means? That whenever you introduce a medium other than free space between the two charged particles, the electrostatic force of attraction or repulsion between them decreases. This is the result. So as you see, we have done this part also. That is the relative permittivity or dielectric constant. Now, in for the vector form, as I told you, that is the Coulombs law in vector form. As I told you, that is important. Coulombs law. Coulombs law in vector form. In vector form. Why? Because here you have to deal with that sense force as a vector quantity. So we need to deal it in terms of force. So the electrostatic force of attraction or repulsion between the two charged particles in a vector form, how I can express it, it will be K Q1 Q2 by R square. So you see this is a magnitude. So in order to express this in a vector form, what I'll be writing K Q1 Q2 into R square into what? Into, that is a unit vector, where R is a unit vector along the line joining the center of the two charges. And you know that a unit vector is always equal to a position vector divided by the magnitude of that vector. R, we can write that the vector, unit vector into what? Oh, sorry, I don't
Here's
need
what
it.
I found online. Please look at the screen.
Wait. Sorry for that. Okay, so you just see, look, is, you know that how I can do it like this. This is what it is in the vector form. Now, in order to calculate the force along its direction, you need to find the position vector between the two charged particles first. For example, let us suppose if you have the two charged particle, for example, you have this charged particle as Q1, right? And if you have another charged particle, let us say, for example, this charged particle is Q2. Let's say, for example, this is positive, and let's say this is a negative charge, right? Then how you can find this position vector? This is important. The best part is, for example, if you just want the force of charge Q2 due to Q1, so look, this is so easy. You just do it like this. For example, mm, let me do it like that. Let me do it this way. Shapes like that is this one. For example, in the 3D case, like this, as you see, look, as you see, look at this. This is in the three. Let me do first, do it for you in the two-dimensional plane. Then later on, once you understand, then I will show you how to do it in the 3D plane. So let us do it for this one first. You just see, Look at this. This is the charged particle. So this is your x-axis, this is your y-axis, as you see. Now what will be the position vector? The position vector will be, now the position vector will be this one, as you see. And you know, look, this is what, this is the position vector r12 along the line joining the center of the two charged particle. And you know, this is what r x, and you know, along the vertical this is ry. And definitely your r vector, it will be equal to rx along the x-axis, ry along the this is a unit vector along x-axis, this is a unit vector along the vertical axis. So you see, this is the position vector. So that is how you can find the value of this r12. So now you see, look, going back, as I told you that this you can also write it like this, fk q1 q2 into r square. And you know what is this? This is a position vector r. And you see, look, what is this? It will be like, this is r. So it will be, this force vector will be k q1 q2 r q into what, and what is that? This is this position vector r, this vector, as you see. So now you see, this force F, it will become equal to what? K Q1 Q2 into R cube. R is the magnitude, and you already learned this in class first year. Rx square plus what? Ry square under the root, like that. And you see, this is what? Rxi plus Ryj, like that. So that will give you what? That will give you the force along the x-axis and along the y-axis. So this is what? This is the force in its vector form, right? This is for two-dimensional plane. For 3D, you can add another coordinate also. So much of the numerical related here is based on the vector form, right? So let me check your book if I, maybe there might be example 11.2. You just see example 11.2. The 11.1 is very easy. It is of the class 10 standard. So you 11.2, you just look for the 11.2 and you study 11.2 and then ask me that whether you understand that or not. So this is our today lecture. And our this today lecture, I explained to you the Coulombs law and the few important points regarding the Coulomb law. First of all, we have developed a mathematical relationship for the electrostatic force of attraction or repulsion that exists between the two charged particles when the two charged particles are point charge, point stationary charges, right? Point stationary charges. I'm so sorry, I forgot this in the beginning. Charges must be stationary. Why? Because if they are not stationary, the distance changes and the Coulomb law cannot be then applicable. Then for the material medium, then I told you the about the permittivity, the relative permittivity or the dielectric constant, and the Coulomb's law in the vectorial form. That how we can express Coulomb law in a vector form. So this is our today lecture. Hope you might have learned from the today lecture, right?